Hey guys, this is going to be your trimester review. Let's begin with a couple practical considerations. Number one, don't stay up all night studying. That's just going to put you at a disadvantage when you're really tired and you're not going to be able to recall the things that you didn't give time for sleep to encode. Secondly, get a good breakfast in your stomach before you come to school tomorrow. No sense in being hungry for 3 hours. Make sure you use the bathroom in between exams. And you guys will also be in room 101. Remember, that's a regular classroom, so go in, find your seats real quick, and listen to the proctor. All right, so once you get those things out of the way, when you actually get your test, the first thing I always recommend students do is read through the part 2s and the part 3s. Some teachers will tell you to do that stuff later. Go right to that, start reading through, make a game plan. Your part 2, part 3 is worth 30% of your grade. Now that's not to be afraid of it. It's to say, hey, that's really important. Let's not rush that. Let's get that out of the way at the beginning. So start reading through, figure out which sections and which questions you want to answer, and that way when the bell rings for the start of the exam, you go straight there. Now when it comes time for you to go through the part 1, remember my test-taking rule of if you don't know the answer within 10 to 15 seconds, box the whole question and come back to it. At that point, stop touching your Scantron. You're more likely to make a mistake when you skip a question, but you forget to skip it, you screw up the whole Scantron. It just causes a lot of headaches. So do yourself a favor, box it, come back to it. At that point, you will have seen the whole exam. You guys should keep yourselves at a good, comfortable pace, and I'm sure you all are going to do just fine. All right, now, if this document that we're about to go over is the only thing that you've studied, I'm a little nervous for you. All right, hopefully you've come to the extra help sessions, you've gone through all the trimesters, you've gone through all your exams. This is just something to get you thinking. So there are a couple things on here, certainly not going to be on the exam, but other things that will definitely be on the exam. The idea is to keep you guessing and keep you out there reviewing. All right, so vocab, it's on the screen. I'll let you guys pause. You can click on my website to find this video. So I'll let you pause it and go through the vocab. I think it's pretty straightforward, things that you guys should know. Now, diagrams are super important. I think I've belabored that point this year. But when you take a look at a diagram like the phases of the moon, the first thing that you want to be doing is you want to look and go, okay, where's the sun, right, which is all over here, where's the earth, and then the moon has to be the one that's right in the middle. That is always going to be your new moon phase. New moon. If you can just put it in your mind, new moon phase every single time, then sing back the song in your head and you can label the whole rest of the diagram. Alright, so just underneath that, remember that the moon rotates at the same rate that it revolves, which is why we only ever see one side of the moon. Too easy. The only way you see the other side is obviously to get in a space shuttle, and that'd be pretty cool. Alright, next, some evidence that for the big splash. Remember we talked about the different ideas for how the moon may have formed. Maybe it was a captured asteroid. Well, if it was, it wouldn't have such a nice round shape. If it was a captured asteroid, its composition wouldn't be so close to that of Earth. But when we look at the composition of Earth, the fact that the moon has a little bit less iron, because if something smashed into the Earth, probably blasted a lot more crustal, mantle, rock out, not so much iron. You'd have a really small iron core, and then a composition similar to our crust. We'll get into the actual densities of all that stuff when we do plate tectonics. But as a general rule, Earth's density is 5.5 grams per centimeter cubed, the moon 3.3 grams per centimeter cubed. That iron concentration comes in as a factor. And then of course the age being 4.5 and Earth being 4.6 kind of would make sense that if it smashed in, all these different lines of evidence tie together, get you thinking, big splash. Good. Now, a little more vocab, but there was definitely a typo in here. I left off sidereal day. I think ecliptic ended up on here twice. You guys can look this down later on. Again, videos on my website. I don't want to spend time reviewing vocab. Perturbation will not be on your exam. Perturbation will not be on your exam, so don't really stress that. Good. Next. Over here we have a little picture of a mineral with 3 perfect cleavages making a cubic crystal. So that instantly comes to mind halite, galena. If it was calcite, obviously it would be a rhombohedral crystal. If it was mica, maybe 1 perfect cleavage, but it would look like sheets. If it was quartz, it wouldn't have any cleavage. So what we're looking at there, definitely be thinking if there are arrows pointing at a break, a nice clean break, along planes of weakness, we're looking at cleavage. Now this diagram, again, for the sun, good diagram to look at because it gets you thinking about all those different components. I can't guarantee a diagram or not a diagram, but if you guys go through each diagram and make sure you can define them, label them, you understand how the different parts work together, then you're going to do just fine. So we got the photosphere. Remember, that's the visible surface of the sun. When we move inward from there, C is showing the convective layer, the radiative at B just below that, and the core at the center. Remember, the core is where nuclear fusion is going to be taking place, where you have the hydrogen bonding into helium. Talking temperatures over 10 million degrees Kelvin. That's going to radiate outward all the way up to the photosphere, back at A. Remember, that's the coolest layer. Just above that is the chromosphere, which chromosphere and corona we can only see during a total solar eclipse. And that chromosphere is also where you're going to see features like H, which is the prominence, that arc of material that's blasted out and pulled back down. When 2 arcs come together, boom, we get a big solar flare, and that sends all kinds of charged particles called solar winds all the way out into space. Awesome. The corona, then represented by G. Again, you're really only going to see that during total solar eclipse. Can't stress that enough. But pretty cool. That's actually going to be the hotter of the 2 atmospheric layers from the sun. All right, and then down here it talks about hot spots. Remember, Galileo saw the hot spots, proved that the sun rotated, also made him blind, staring through his telescope. But they tend to come in pairs, and that's where the convective loop breaks through the surface, usually comes back down. If you can see that outline, that's the prominence. Okay, I think I hit enough on the sun. Let's keep going. Seasons diagram, seasons diagram, seasons diagram. Gotta know it. I mean, it'd just be crazy not to. And again, a quick little cheat. Find where the North Pole is pointed toward the sun, and that's always going to be June 21st. Where it's pointed away over here is going to be December 21st, right? So this is actually what we're coming up on. Remember that as we approach December 21st, just shortly after that, we're going to hit perihelion, when we're actually closest to the sun. Back on July 4th was aphelion, just little points in the orbit. Remember the elliptical shape. But let's get back to the diagram. When you can figure out where June 21st is, you know that's the summer solstice. You know that's 24 hours of day at the North Pole and 24 hours of night at the South Pole. 90 degrees of insolation on the Tropic of Cancer. Then just move it counterclockwise, and you should be able to fill everything in. So if that's June, the next big point that comes up would be September, and then December, and then March. Remember, 3, 6, 9, 12, it all seems to work. Other details. When I look here, I say on the sides are going to be my solstice, and top and bottom in here, right, this is going to be my equinox. If that helps, breaking it down, remember that you could have a diagram that basically flips everything, so then north would be like this, right? And at that point, that just becomes June. If I just confused you, forget what I said and move on to the next thing. All right, down at the bottom, tides. Tide diagram is kind of cool, but the biggest thing is when the sun and moon and earth all line up in one line, you're going to have the greatest tidal range, right? Really high tide and then really low tide. That's going to be your spring tide. So spring, think strong, everybody's pulling the same plane. Neap is going to be the neutral tide. That's where the moon would be perpendicular to the sun-earth lineup, and therefore it's trying to pull one way, the sun's trying to pull the other. You don't really get much of a tidal range at all. All right, now there's one little typo, I think, in here for Houston, but just take a look, doing longitude, latitude, this is in all degrees. Remember that degrees could be divided into minutes, and minutes could be divided into seconds. That being said, I don't think you're going to see anything much harder than this. Just below that are your different types of projections. Please go over them. Please remember that all projections have distortion toward the edges. The best example or best projection would be a globe, but we certainly going to have issues with trying to carry a globe around if we want to go hiking because you can't find yourself. So instead we have these different types of projections. The best one for the U.S. would be a conic projection. That's a little party hat because it's going to get the mid-latitudes. The gnomic, just a little flat point. Wherever that's touching, in any of these, wherever the projection's actually touching is where you're going to get really good detail, and then as you move away from that point of contact, the detail lessens. All right, so you guys can see the notes there, but I think I hit the key points. This last one over here seems to be giving a lot of people some trouble. So this was there on purpose because I wanted you to review the vocab. Do you know what a proton is? Do you know what a neutron is? An electron, an isotope, what the atomic number and what the atomic mass are. So real quick, this is your atomic number. It's always going to tell you the number of protons and number of electrons that you're going to have. Then, let me just fix that real quick. Sorry about that. Then you have your atomic mass. That's always going to be the number at the bottom, right? So that's your atomic mass. Well, how do we figure out the atomic mass? Well, by definition, it's the number of protons and neutrons in the nucleus. So if I know that I have an atomic mass of 19 but an atomic number of 9, well, I subtract 9 from 19, I end up with 10. And hey, that's the number of neutrons. Too easy. But if somebody asks me about an isotope, I know isotope by definition is an element with different numbers of neutrons. So it's the same element but different numbers of neutrons. And here it's saying plus 2, which means that if I have to add 2 neutrons, I'm going to go from having, oh, sorry, there's a typo on here. My apology. Ooh, this is wrong. That should actually be 12. Sorry about that. Ooh, good catch. And that then brings me from a mass of 19 up to a mass of 21. Sorry about that, guys. Trying to get it done. Next, let's look at the solar system, right? Remember M, them, J, sun? Well, M, them are going to be my inner planets, right? My rocky planets, my terrestrial planets, and then J, sun are going to be my Jovian planets, my gaseous planets, all of which have rings, all of which are going to be huge by comparison. And why are they huge? Well, because gravity wasn't as great on the gases, so the gases all were able to move to one part. Gravity was much stronger and kept the smaller planets inward, gave that little like crumb layer at E of the asteroid belt, and then the icy layer of K with the Kuiper belt. That distribution, all because of gravity, it's a beautiful thing. All right, nothing would be complete without the life cycle of a star, right? Whether it's in question form, definition form, or a diagram, you gotta know all stages. So remember, stars begin as a cloud of interstellar gas and dust called a nebula. When it starts to compress, starts to heat up, we call it a protostar. When it gets hot enough, over 10 million degrees Kelvin, hydrogen to helium nuclear fusion begins. You are now a main sequence star. All right. When you run out of hydrogen, now you have a core of helium. Where that line is, that's where you're going to cross, and now you're either going to become a red supergiant or just a red giant based on your mass. Medium mass on the bottom and massive on the top. But we know the fate of a massive star is going to be an iron core that's going to collapse, kaboom, make a huge supernova, and then if the mass is less than 3 times the mass of our sun, you get a neutron star. If the mass is greater than 3 times the mass of our sun, you get a black hole. But our sun, of course, a medium mass star, so it's just going to become a red giant. Once it stops fusion, usually it's left with carbon or oxygen. You're going to have this core that's trying to collapse and compress, which eventually becomes a white dwarf. The atmosphere burns off. That's your planetary nebula in the transition phase. And to be a good scientist, we know that things that are hot have to cool off. So we would actually our sun will end as a black dwarf, which isn't shown in this diagram. All right, and then some simple topography. This is basic review. Yours should look something like this. Yours should look something like that. And please don't forget units. Please do not forget units. All right, guys, that's all I got for you. Spend the rest of the time reviewing. If you have any questions, feel free to email me. Check out the videos on my website under Earth Science tutorial videos, and do your best. All right, y'all are awesome. Merry Christmas.